Hi, in this video, we want to take a look at preliminary analysis of a point pattern. Okay, so what we've got going on is I have points in some area, some region that I'm interested in on the ground. So this might be like for ecology, this might be a disease study, but I have location and I have an observation of an event that is of interest. And I want to run statistical analysis of this. Okay, so what we want to do in this video, we want to take a look really just at a probability distribution assumption and what that theoretically gives us after that when we make this assumption. All right, so what we're going to do, we're going to take the point of view that the probability distribution is uniformly distributed for these points. And then we're going to take a look at what happens. What do we get for free theoretically when we're using the assumption of uniformly distributed points in the region of interest? After that, we'll look at one particular way visually to check to see, does theory match up with the data I have in front of me, so that I'll be able to say yes or no if the data I observe is uniformly distributed. Okay. So usually when we're dealing with points on the ground, and that's my data set. So my data is, I know the event and I know the location. That's all I've got going on for this problem. All right, we're going to be interested in the distribution of the events in the region that we're talking about and the possible existence of interaction between the points. Okay, so think about this. If I'm talking about a disease, then I could have one person distributing the disease among many people. And if there isn't a whole lot of movement going around, then I would see that the people with the disease will be location-wise close to each other. Okay. Another situation I might have is, let's say we're talking about animals that have territories. And so in one region, I have one animal, let's say one male bear. I'm just going to say a bear, but one male bear. Over here is the territory of another male bear. Well, they're going to compete with each other. They don't really want to get hurt, so they generally avoid each other. And that system will make it so that the points are more spread out than we would expect under the uniform distribution assumption. All right, so if I look at what I've got and I see clustering, then I know I don't have uniform distribution. Or if I see things are very well evenly spread out, I know I also don't have uniform distribution. All right, so when we talk about spatial randomness, two extremes that we could see is that our points appear to be in clusters, or they could follow a regular pattern. All right, so when we see clustered patterns, this is usually when there's something like that, kind of attraction between points that makes it so that they're kind of clumping up. If I see regular patterns, then probably what's going on is there's some mechanism for inhibiting them from being close to each other. So such as a competition, between whatever is going on for those events. All right, so the first way that we're going to think about this is we're going to start by visualizing what's up. So let's go ahead and visualize the data that I went over for 7.2. We're going to look at the distributions of some trees. Now, in this document, I've already loaded the data set, and the code is in the 7.2 video. But there are cells, there are Japanese pine trees, and then there are redwoods that are in the sample space. All right, well, after loading the data, let's go ahead and put it all into one data set, which I did. And now let's visualize this using lattice so that we can see what's going on. All right, so to visualize it, I'm going to use the lattice XY plot function. I'm going to say that it's a scatter plot, Y depends on X, and we're getting things from our data sets, but the data frame, spatial points, this object here is specifying the data that I'm putting in. This column in the data frame specifies where the individual observation comes from, which tree it is. Is it cells, Japanese, or redwood? And then here, this is the solid point character. And then I want to make sure that things are an aspect ratio of 1 to 1, because that's how coordinates are in real life. Okay, so let's take a look. All right, so you can see that we've got cells, Japanese, and redwood. So when I look at the cells, I mean, that's, there's some randomness going on, but I see that none of the points are like coming together. None of them are really close. They're all kind of uniformly separated out. Over here, sometimes they're close together, sometimes they're not. There doesn't really seem to be any system to what's going on. Well, like over here in the redwoods, I see a lot more grouping. All right, so this leads me to, with my eyes, have a hypothesis that the cells are regularly distributed. The redwoods have some clustering going on, so neither one of these are uniformly distributed. And then in the middle, I'm going to run I have the hypothesis that the Japanese pine trees are uniformly distributed. All right, so now I've got somewhere to go, something to analyze, something to work with on this. So now what I want to do, I want to actually have a probability distribution so I can actually run proper statistics and start doing some more rigorous testing. Okay, so what we're going to do, we're going to figure out the distance to the nearest event. All right, so this is going to be like a nearest neighbor distance function. So here, this is event to event or inter event distribution. So I want to know something about the distance from an event to its nearest neighboring event. All right, so I'm interested in the minimum. So given any particular point, I want to know what is the distribution of the distance to its nearest neighbor. Okay, so let's go ahead and work this out. So first of all, I need to define what is my distance. So the distance for observation I is going to be the minimum distance between that event and all other events. So notice that, so this is the distance between observation I and observation J. I take the minimum of this with regard to J, and then that is going to be the distance from I to its nearest neighbor. Okay, well, how do I approximate this? Well, so if I'm going to be making a function, what I can do is I can say the number of, for any particular radius I'm interested in, I can look at the number of points who have this minimum distance is less than or equal to that radius, and then divide by n. So I know it's going to be, a fraction, and that's going to be my g hat function, and that's going to be my nearest neighbor distance function. Okay, well, it works out, if I work out the mathematics of this, for some minor assumptions, that this function is going to be approximately equal to this one under some minor constraints, minor assumptions. And so this is going to be 1 minus the exponential of negative lambda times pi times r squared. So pi r squared is the area of a circle. That should not be surprising, given that we're talking about spatial things and on a plane. Okay, so now let's work out the derivation of this g function. Why is this a reasonable function to be using as a way to have a probability distribution for the distance between a point and its nearest neighbor? All right, well, I'm going to go through the derivation. Without loss of generality, what I'm going to do, I'm going to go ahead and just say that my reference point is at the origin, because I can always set up my coordinate system with a point of interest being at the center. So I just go ahead and do that, make it a little bit easier. Now, then for any given j, so any given other observation, the probability that the distance between the reference point and the one of interest is just going to be literally the distribution probability that the distance is less than or equal to r. Well, that's going to be the probability that x sub j squared plus y sub j squared square root is less than or equal to r. Well, I look at that and I realize, well, that's just, the circle centered at the origin of radius r. All right, well, we're talking about uniform distribution for my points. Therefore, I know that the probability is proportional to the area of the circle. All right, so I know that the probability is going to be proportional to pi r squared. Easy peasy lemon squeezy. Haven't really done much yet. Now, uniform distribution, I know that I need to have the total area that I'm talking about has to be probability 1. So that means that I need to divide by the total area of interest. All right, so now I know that the probability that the distance between two given points being less than or equal to r is equal to pi r squared divided by the amount of area in the region of interest. Okay, so now I'm going to do something surprising, something a little bit different. I'm going to change this a with n over lambda. What's going on here? Well, lambda is going to be the population average number of events per area. So this is like the rate of events per area as a parameter, and n is the population average number of events in a region of area A. Okay. And so here, if you just do a little bit of, basic arithmetic with this, you know that A is equal to n over lambda. All right, and then of course I just simplify that fraction nicely. All right, so now that tells me the probability distribution for any 2 points, the distance between 2 points. What I actually want, I don't want from a reference point to a particular one. I want a reference point to the minimum with all the other points. So I want the distance from the reference point to its closest one. I don't care what the subscript is. Okay, so what I'm going to do for that one, the probability that the distance from reference point I to its nearest neighbor being less than or equal to r, well, that's going to be equal to the probability that the minimum of what's up here is less than or equal to r, right? Okay, not a problem. Now, I look at this and I realize that, well, I want to do order statistics. I want to use order statistics from my most basic math stat course. And I know that I don't want the minimum on the left-hand side of R. Okay, so notice what I do next. I want R to be on the left of the inequality and the minimum to be on the right. Why is it that I want this presentation? Well, if the minimum is greater than or equal to R, that tells me that all of them are greater than or equal to R. Okay, so by putting the minimum on the right-hand side of the inequality, I know that all of the Dij's are to the right of R on the inequality. Okay, well, to get this, I know that if the probability of the minimum is less than or equal to R, that means that 1 minus the probability of R less than the minimum. So remember, I'm just switching it. So this number plus this number adds up to 1. Therefore, I know that this has to be equal to 1 minus that. All right, and that gives me the minimum on the right-hand side of the inequality. All right, well, the minimum being greater than R tells me that every single one of those distances is greater than R. All right, well, that tells me that this is going on. Now, I'm going to use the assumption that the distance between I and 1, in distance between reference point I and point 2, the distance between each of these are all independent of each other. As long as they're independent of each other, I can break up this probability statement into the product of smaller probability statements. Now, I'm going to make the assumption that each of these has the same probability. If they're all the same probability, because I'm assuming that each of the dij's have the same distribution, then this is in fact the same thing being multiplied by itself a bunch of times, which is better known as taking a power of something. Okay, so now I've got this simplified pretty far down, looking good, feeling good about this. Now, what is going to happen is that this isn't quite the format that I want. I'm looking at that, I'm like, oh man, I've got, an exponent here. How do I, clean this up a little bit? Well, what I'm going to end up doing is I'm going to do exactly the same trick I did up here. I'm going to use the 1 minus trick to convert or to put things on the other side of the inequality. All right, so now I'm going to do this. And you'll notice it's inside the power. Okay. So now I know that this is going to be equal to that. Okay, so if I take this and I put it into this position, I see something, I go, hey, that looks a lot like something from Calc 1. All right, so it's going to work out that as long as I have a sufficient sample size and n minus 1 is approximately equal to the average number of events over region of size A, then with this here inserted for that, then this whole thing is approximately equal to the exponential function with negative lambda pi r squared. Okay, so how do I get that? When I put this in here, down into this position, you'll notice I have a capital N on the bottom, and I have an n minus 1 up top here. All right, so when n is approximately equal to n minus 1, then this whole thing is going to be approximately equal to the exponential of negative lambda pi r squared. And so this was going to be pretty close. I should have an approximation symbol right there. I made a mistake. I meant to put that there. All right, so here, this probability is approximately equal to this function. Okay, so that's good. So now I have something that is approximately equal to the probabilities. So what I'll do to make my life easier when I do the analysis, as long as I remember that I need to have uniform distribution, I need to have a sufficient sample size, and I need to have the number of points be close to the expected value for the population of the average number of events in a region of size A. As long as all those things are coming together, I can just say, hey, this is my probability. And I know it's a little bit off, but it's close enough that I can run my analysis. Now, when I say n minus 1 is large, that can come from either lambda being a larger value, or that can be from the area being larger, if I'm sampling from a large area, or it could be from both of them multiplied together, giving me a large value. So if I had small lambda, it's okay if I have a big area. If I have a small area, it's okay to do this approximation if I have a very large intensity for the point pattern, a very large lambda. but I need to make sure that I have this product is relatively large in terms of the convergence of the exponential limits for me to be able to make this approximation reasonably. If it's too small, then I need to do something that is more specific to a small sample size analysis. All right, so here is the probability that I get without considering the exponential, and then this is the actual exponential itself. All right, so now let's go ahead and let's come up with a way to evaluate, is a uniform distribution on the points reasonable, yes or no? All right, so what we're going to do is I'm going to take the envelope function in stat core, and I'm going to run a bunch of simulations. And with the simulations, I'm going to get an interval of values. And so with those observed intervals, if I see that my data is matching up with the theoretical aspect, then I can be very confident that what I'm looking at is uniformly distributed. So what I'm going to do is I'm going to simulate repeatedly over and over and over how things would look if I have the uniform distribution. All right, so I'm going to take each of the three sub data sets I have, cells, the Japanese pine trees, and the redwoods. I'm going to run a simulation that corresponds to the sample size of each one, and I'm going to run that simulation assuming that I have a uniform distribution. If uniform distribution matches the data, then what I observe should be close to what I see in the data. All right, so how are we going to do this? I'm going to work out all of the various radii going from 0 to square root 2 over 6, and we're going to make incremental increases by 0.001. Here I chose to run a simulation. Each one will have 1,000 simulation runs. And what I'm going to do, I'm going to take the spatial point pattern. So planar point pattern here. I'm converting the spatial points to the point pattern. Now, what I'm going to do, I'm going to randomly generate what's going on here uniformly over each of these R's, or I'm going to compute what I should see here for each of these R's. I'm going to do that for each of the three observed data sets. So now let's go ahead and visualize what's happened. So what I'm going to do, I'm going to take the three different data sets, I'm going to drop them into lattice XY plots, and then I'm going to hit the print button. Okay, so what I've got here, let's look at Japanese first. This gray area, the vertical slices, so everything is in terms of the vertical slice. The vertical slice shows me that under the unit, so I made a simulation using the uniform distribution, and each simulation matches my Japanese pine tree data set in terms of like its size. All right, so what I did for each of the runs, it goes through, it generates random data using uniform distribution. Then for each radius value, it computes on that simulation how many points are within the radius. All right, and once it does that over and over and over, and I get an observation interval for like 95% of the observations are inside this range. Remember, everything is vertical. So if I see that my observed data is completely within the gray region, then I am confident that I have uniformly distributed data for my spatial point pattern. So here, when I look at the Japanese pine trees, I conclude, yeah, that's probably consistent with uniform distribution. Here it bumps out a little bit, but that's close enough that I would personally, if I was working on this at work professionally, I would accept this as uniformly distributed. Now, let's look at cells. Remember that cells had what looked like by my eyes a regular pattern. All right, well, in that case, we notice that this curve, which is always increasing, it's always increasing for all three, is like way below, way below. And so, like, definitely this uniformly distributed points assumption does not hold. Look at redwoods. Well, redwoods, I can see definitely is veering away from the distribution. So I conclude that once again, that redwood is not uniformly distributed. Now, another function is to estimate the empty space function or its hazard rate. All right, so here we're talking about the spherical contact distribution or the point to nearest event distribution. So previously we were talking about event to event. So point in the data set to its nearest neighbor in the data set was the previous thing that we're talking about. Now we're talking about I'm at any point in the region of interest. I want to talk about the distribution to the nearest event from a point. Now that point may or may not be in my data set. Now it works out that the mathematics gives me the same approximation, and which isn't really that interesting, but my F is going to be of the same. So I'll scroll up here to it. The F of R ends up being the same as our G of R, like this. And so that gives us something to work with. So I'm going to do exactly the same game plan. For each of my sub data sets, I'm going to go through, do a random generation of data using uniform distribution, compute the F every single time for all these different radii, and then I'm going to get an idea of what the distribution would look like if uniform distribution is the correct distribution. And I'm using the envelope function to knock this out. This is actually a pretty powerful function. When I plot it, this is almost the same exact code for plotting as I had before. And I can see, all right, so for the Japanese pine trees, that's fitting really, really tight. When I look at cells, all right, so cells, it's going in, it's too high over here, and redwoods is too low. So I conclude that the Japanese pine trees look like they are uniformly distributed, at least strong enough evidence for me to proceed with that. But cells are not, and redwoods are not. All right, well, that's all I've got for you. Take care and goodbye.